Any questions? There's myself here today, and also my colleague Daniel will be running around as well. Also, if those of you that have just arrived, if you need the Wi-Fi, it's level 39 visitor, and there's no password required. The gents' toilets are just down there and to the left, like the other side of the lift. Yeah. But yeah, I really hope you enjoyed today, and yeah, please make sure to give us some feedback as well.
One quick addition, if you guys, the idea is for you to network with Intel specialists. So all the Intel specialists, if you can raise your hand. So
Intel specialists.
Yeah, at the back of the rooms. Don't feel free, just grab us, come on us, and ask all the questions that you have in mind. This is the time, this is the place, that we have the opportunity to do that. All right? David, all right.
Thanks very much. Okay, how are we going for microphone? Son? Cool. So, hey folks, welcome to the Software Development Day. We're very pleased to have you all here. Thank you for the excellent turnout. My name's Dave Halliwell. I am the technical lead for engagements here in financial services for Intel. Some of you I've probably met before, but there's a lot of new faces I haven't seen. So if anyone wants to contact me, davidhalliwell.intel.com is my address, and I'd be happy to engage in any way, shape, or form. I'm going to talk a little bit today about our public hardware roadmap and software enablement, optimizations for the upcoming Intel releases. Now, because it's a public space and Intel is quite protective of this information, there's not a lot of, you'll see some slides are a little bit sparse. And if at some stage people with black masks having to jump through the windows, that's the Intel lawyers coming to get me, because there will be some things I'm saying that are going to be a little bit risque in terms of where we're going with our roadmap. With that, I'm sure you're all pretty familiar with our kind of general product line. Intel's strategy at the moment, as you can well imagine as a hardware manufacturer, is to optimize runtime workloads effectively as much as we can. Much of this optimization goes into enabling orchestration and administration and architecture of the data center space, as you could well imagine. But also lots of this goes into how we enable software development and in particular workloads of a specialist nature such as HPC, what we generally call AI, and other more technical oriented workloads that give some tremendous business value to what we're doing with our software applications or just generally in our operation of our business. So I'm going to walk through effectively a couple of technologies here. Some of them are quite new. I'm going to start with some new hardware, or some hardware that's effectively available at the moment. Then I'll go into some new hardware, and then I'll go into some of the enabling tools that come in as a result of the rest of the things that I talk about. So this is one of the slides that looks a bit sparse at the moment because I can't talk too much about what's coming in the future. But effectively at the moment we have delivered our Cascade Lake CPUs, which are the fundamental workhorse of data center compute at the moment. And one of the major software enabling tools that we introduced with this is the AVX512 and FMA extensions to the instruction set with the x86 processor type. And we've also introduced a new memory hierarchy with the Skylake and Cascade Lake scenario, or the CPUs as well. The first of those being completely revamped cache architecture. If you're not familiar with the changes to the cache architecture, I suggest you have a look. It's readily available online. And effectively what we've done is dramatically expanded level 2 cache and slightly reduced formerly what was level 3 cache, into I guess a much more what we feel is an optimized architecture for people who are trying to fit data structures or tune their cache workloads in order to get lower latency performance or better optimization of the memory architecture. The other major memory component that we've adjusted, particularly with Cascade Lake, which is our latest release, is the data center persistent memory. Anyone who's talked to an Intel representative or someone from the company, or perhaps anyone from Tech Press in I guess the last, maybe 5 years, I suppose, has probably heard of data center persistent memory at some stage. Intel's renamed it a couple of times. Its generic name is Optane. What effectively we've done is release that persistent memory, very, very dense memory in a DIMM format, which means that we can actually modify application architectures considerably to take advantage of this. Database, big data, and AI are some of the major workloads that we're enabling for this technology at the moment, and we're integrating these in a number of ways, either as a big memory footprint or as a very fast cache device that is persistent. Coming into next year, we have a number of new platforms coming out, Cooper Lake being one of these. This is going to be a platform optimized for HPC and AI, scaling up to what we consider a large core count, and effectively it brings in a particularly useful new training floating point structure called bfloat16. This was first introduced with Google's TPU several years ago, and it enables effectively a 8-bit exponent and a smaller mantissa that is going to fit in the same size as a bfloat16. So if you use a floating point 16 rather than a floating point 32 for a training purpose, effectively what you're trying to do is build up your throughput or expand your throughput considerably, because we would normally use floating point 32. The problem with that is it takes a very long time to load up these registers and process the data. If we use floating point 16, we get much lower dynamic range. But with bfloat16, we can get exactly the same dynamic range as 32, floating point 32, but we can also double our throughput. So this is an optimization for training, and it is considerably, what we're testing at the moment, high performance optimization that we're seeing in these particular processes, targeting basically the ability of Xeon workloads to take on, I guess, ideas and practices that we would normally target at heterogeneous devices such as a GPU or a custom ASIC or so forth. It's still not going to be perhaps as high performance as some of those devices, but probably good enough for many of the workloads that we see out there. Concurrent effectively with Cooper Lake in next year, the later part of next year, we have our Ice Lake CPU. This is going to come out with some security enclave features that you may have heard of, such as SGX, memory encryption, which we call MKTME. It has a number of variants. We can do it at the VM level, we can do it at the system level, or we can do it at the application level. It will come out with PCIe 4, and it's going to be Intel's first 10 nanometer CPU in the data center space. So we're quite excited about that. The following stuff, the Intel legal people wouldn't let me speak about at all. It does contain some stuff, and you might get glimpses of what is in store when we talk about the things in the roadmap, particularly with Compute Express Link, the requirements for things like Compute Express Link. For those of you who don't know what Compute Express Link is, it's effectively a PCIe 5 implementation or a bus protocol that runs over the PCIe 5 interconnect that takes advantage of that bus, but also implements much faster registers, much faster buffers, memory interconnects, and much higher throughput as well. And that enables a whole range of stuff that's coming down the pipe as well. So you can kind of guess where that's coming in if you have a look at the bits that are left out there. The first of our optimized processors was announced probably about a month ago now. Nirvana was an acquisition that Intel made probably about 2.5 years ago. Their whole, I guess, reason for being was to build incredibly fast, optimized, you can think of it as kind of an ASIC for AI training and inference. They then developed a much more flexible platform that Intel optimized and brought to market and landed about, as I say, a month ago. What we're targeting here is competition with the very large, custom designed implementations such as TPU, Facebook's options, so on and so forth. This is going to be a large-scale deployment for really, really big customers that we see are working with training and inference workloads in the data center space. One particular implementation, which is the inference, the NNPI device you can see here, is actually quite a small form factor M.2 device that we can stack 32 of these into a 1 RU system to get incredible throughput for inference workloads. And as a result, the performance per watt, the performance per rack space for these particular devices, it far outweighs anything that's on the market today. And I encourage you to have a look at these devices. There's information from Intel on the web if you're interested in looking up this material at all. The next of our optimized devices in the data center space is another acquisition from Intel. And funny, acquisitions are something that probably is a little bit of a theme of this presentation. Intel acquired an FPGA manufacturer called Altera, probably again about 2.5 years ago, and as a result has worked with Altera to bring to market a number of FPGA optimizations in a PCIe form factor for customers working with high throughput and low latency workloads. The latest in that development is the Agile-X FPGA. This comes in a number of custom formats. We're able to make, it's quite a modular design. We're able to make a number of kind of implementations of this device by interchanging the add-ons to the side there and basically making this quite a flexible device to deploy. For those of you who are not familiar with the FPGA paradigm, I'm guessing most of you are, but basically we're talking about a field programmable gate array, quite a spatially oriented device that allows us to program and reprogram clusters of switches in order to implement a specific algorithm, which we can then perhaps redeploy or reprogram when we change our algorithm or we want to change the nature of what we do with that particular device. And they're very well known for being able to achieve very high throughput and very low latency. And it's something that Intel is working quite heavily with. One of the problems has traditionally been the cost of developer time. They typically have been historically quite difficult to develop and more particularly debug on. Intel has invested a massive amount in order to get not only kind of the low-level development tools, but tools with OpenCL and a little teaser, what the forthcoming One API interface in order to work with these devices. Another acquisition that Intel made probably about 2 years ago now, we hired the head of graphics development from AMD, a guy called Raja Kaduri. I think he was working at Apple at the time. Oh no, he came directly from AMD. We also hired, subsequent to him, a developer or a systems developer, an engineer called Jim Keller. He was also the one responsible for the initial design of our AMD, our competitors' Zen microarchitecture. He came to Intel because he thought it was a particularly exciting opportunity with the roadmaps and developments we have in store. And those two together have not only worked together to build a new Intel roadmap, but also a graphics offering. And Intel announced about 2 weeks ago now that we would be entering the GPU space in the data center. And effectively, the plan was, and the plan is, we've been developing integrated GPUs for quite some time in some of our data center SKUs and many of our, I guess, consumer offerings as well. And over that time, we've been able to integrate and tightly package quite a lot of silicon and capability into very small components. With the hiring of some experts from other industry or from other organizations to bring in a capability, Intel has now got to a Gen 11 space where we have released our first discrete, or the first in a long time, of discrete GPUs that are effectively going into the cloud space at the moment, enabling things like cloud-based gaming, that sort of thing. With the next generation, which we're calling XE here, we are basically announcing our new foray into the data center space for GPUs. The first one of, whoops, gone the wrong way. The first one of these we announced quite some time ago, actually, and it's going to be called Arctic Sound. This particular device is basically made up of some of those Gen 11 architecture tiles and enabled by some Intel, I guess, wizardry that has come in recently. There were some press announcements about an interconnect called EMIB. What this allows us to do is package tiles in a very, very efficient way so that we can scale them in never before seen densities and throughputs. So what we're able to do now is effectively build modular graphics devices, harnessing our Gen 11 architectures and deliver these into the data center space. The first one of these, as I say, is called Arctic Sound. This scales, I guess, in a kind of planar way with the EMIB device interconnect. What we'll see quite some time down the track, can't possibly say when, is a device called Ponte Vecchio, which is going to be a very large-scale HPC-oriented GPU device. This is the first of our devices in the graphics space to take advantage of what we call our Foveros architecture, which is basically a 3D implementation of that EMIB device, which means we can stack in a planar way and we can stack in I guess, a three-dimensional space as well. This enables considerable capacities and benefits to what we're doing with our architectures. I can't say too much about that. Again, it's in a public space. I can't particularly say when. It's probably going to be, I don't know, at least 18 months' time, let's just say that. But look out for this. This is going to be a massive step for Intel in the space, and we think it's going to be something that enables workloads in HPC and AI in a considerable fashion. I've got a little bit to say about Ethernet adapters that we looked at in the first place. Most of this sort of stuff, as I mentioned, for Ethernet adapter space is built around enabling how we deliver kind of virtual devices in the data center. So, how we deliver SROV with Ethernet devices, how we deliver particular orchestration techniques with whatever our tools are. However, we also have implemented 100 gig Ethernet with RDMA, a couple of optimizations for RDMA, both IWARP and RoCE2, so we can get shared memory across our clustered systems, and we can enable very fast and high throughput access through these particular devices, and they'll be coming out next year. But what these will really take advantage of is an architecture that's also coming out called CXL. Compute Express Link, basically, as I said before, is a implementation over the PCIe bus. It basically puts kind of, I guess, a MAC-PHY type device at either end of the PCIe bus that's able to detect what kind of traffic is directed down the line, whether it's a PCIe implementation or whether it's a Compute Express Link implementation, and modify the traffic in the necessary way. And as a result, we're able to implement effectively two bus types over the single physical interface. And with that, we get the ability to do much more efficient interaction and transactions. We get memory sharing, we get cache coherency, all the goodness that you want out of, when you want to plug devices in that are accelerating your workloads, and you're thinking about how we're going to use these, what do they mean? This is basically the medium for the future. Now, this is some time away. However, we already have some devices that are planning and enabled, or almost enabled for this. And as I said, this is something that will be coming in future roadmaps for our post Cooper Lake and Ice Lake devices. So this is something that you should be watching out for. It's going to enable what we call heterogeneous computing. You'll be able to plug in devices, whether it be FPGAs, whether it be GPUs, whether it be the Nirvana accelerators, or potentially any other kind of device, because it's effectively an industry. Well, it's a broad industry standard at the moment. It's being adopted by more and more every day. But that leads us into a bit of a problem. So if we are optimizing for our workloads with specific devices, and we're building unique code sets for each one of these and integrating them into our enterprises, this is all very nice, but we know that as soon as we write one line of code, we're doomed to support it. And trying to support these sort of code sets across these sorts of devices over the longer term is incredibly painful and problematic. Not only that, but we tend to get, if we wanted to redeploy parts of our clusters in order to run the same workload, it becomes a problem because we haven't got similar capability between our clusters if we don't have exactly the same configurations. This leads us to the major topic for tomorrow, which is going to be One API. One API is Intel's solution to, well, we're bringing out a whole bunch of heterogeneous devices. We better make sure that our customers can use them and use them efficiently without, causing unnecessary pain and making it as seamless as possible. So what we've got out is, and this is a massive scale effort for Intel actually, is we've gone out, we said, right, what we'll do is we'll introduce an interface that we can interact with all of these devices, that we can call the optimizations, the math kernel libraries, the specific optimization tools that we have available for deep learning workloads, Intel's deep learning library, so on and so forth, in order to take advantage of the different and heterogeneous types at one time. And this is, as I said, the topic of tomorrow. I'm not going to talk about it too much. In fact, I've pretty much reached the end of what I've got to say today, given the time that I have. I urge you all to go and see Intel's One API session tomorrow. As I say, it is possibly one of the largest scale, I guess, programs that I've seen at Intel during my time there. And I think it is something that's going to be of tremendous value to anyone looking to optimize workloads across all the latest and greatest toolkits and devices that are going to be coming on the market in the next couple of years.
Who is registered for One API session for us?
Cool. And with that, I'm done.
Thank you, Dave.
Thanks, folks.
So now, let's say you use software.
This is good. What do we want? Okay. FPGA.
technical consulting engineer at Intel. So I'm basically doing the bridge between you guys using our tools and our developers developing the tools. So I'm part also of the support, and my main focus are compilers, but also Advisor. And so for this morning, I will talk about Advisor. There will be another session with me later on FP reproducibility. So you might have some concerns, and I will try to give you some tips and tricks to get better reproducibility. So let's start with this presentation this morning. So who knows already Advisor here? Okay, and who knows about the roofline model? Okay. So then we need a complete introduction, I guess. So Advisor is basically a tool that was started back probably 3-4 years ago, and they were mainly focusing on helping developers enabling vectorization in their code. So there was many analysis for that, and it was able to read the binary, detect if a given loop was vectorized or not vectorized, and provide you some hints about what to basically do next. So check dependency, things like that. So for the past years, they added a lot of things in Advisor, and now they're also able to count the number of iterations that you're doing in your loops, to, of course, advise you on vectorization. So you have a dependency test. You have also some tests for the memory, checking how you access the data. And more recently, they came up, so they merged all those data together, and they came up with the roofline model implementation. So before we start with Advisor on the roofline model, I will just explain what is the roofline model in a short presentation here. So basically, the roofline model, this is something that will help you to characterize your application. And it's based on very simple metrics, so how many operations you are doing on one side, and how many memory transfers you are doing on the other side. And based on those, you end up getting what they call the arithmetic intensity, which is a ratio between flops and bytes, and that will help you characterizing your application. So I will give you an example very quickly, and that will probably be clearer. So the assumption that they are doing with the roofline model is this one. So that the performance of your application on a given hardware is limited basically by the minimum between the platform peak, so what is the performance that you can reach on the platform, how many flops per second you can reach, so that's kind of the speed of light. And the second part here, it's the platform bandwidth multiplied by the arithmetic intensity. And we'll go back to that later. So now I just want to show you how to generate this roofline model. Everything is based on this formula here. So how can you obtain this information here, the platform peak? So you just Google the name of your hardware, of your processor, and then based on your system, for example, so that's already an old one that still works the same way. So that's a 2-socket Ivy bridge here. So we have 2 sockets, then the core frequency is 2.7. We have 12 core on each socket. We have 8 single precision that we can put in the SIMD register, so for vectorization. And then on Ivy Bridge, you have on each core, you have 2 ports able to do operations in parallel, one addition, one multiplication. So you basically multiply everything together and you get the magic number here, 1000 something. So that's the speed of light of the 2-socket Ivy Bridge. There is no chance you can get higher than that. And actually you will never hit this performance because there are some security and you are going to also dissipate some heat. So a more realistic value for what you can achieve, you can get it with the Limpack. So you run the Limpack, which is a test used in HPC for benchmarking platforms. And usually on 2-socket Ivy Bridge, instead of 1036, you get 930 something gigaflop per second. So then you need to implement the second line here. So same for the platform bandwidth, you do exactly the same thing. You Google the name of the hardware, you end up on ARC, intel.arc something, and then you get those specifications. So for the 2-socket Ivy Bridge, again, we have 2 sockets. The memory frequency can go up to 1866. We have 8 bytes per channel for each memory transaction, and we have 4 memory channels. And then it gives us 119 gigabytes per second. Again, same problem, you will never reach it. So what you can do, you can use the stream benchmark, and then you get more achievable value here, which is around 100 gigabytes per second. So you have those two numbers, you can start drawing the roofline model. You have 2 axes. The vertical one, this is the performance, gigaflop per second, so number of operation basically per second. And this one is the tricky one, this is the arithmetic intensity. So that's a ratio of operations divided by memory movement, basically. And we can start drawing it. So first, the peak performance is here, so 1036 gigaflop per second. So this line means that no matter what you do, your application will never go higher than that. And then, actually, when you play a little bit with this and those numbers, you see that when you divide the flops by the bandwidth, you get some kind of threshold, which is actually what triggers the different lines here. So, and this ratio here, this is 8.7. So basically, if you are on the right-hand side, that will be this line, the first line that will apply, and you are basically limited by the flops. And now you can draw also the second one. So this is just, you take 2 different arithmetic intensities, you multiply by the bandwidth, you get 2 points, you just draw the line, and you're done, basically. So usually we don't show the origin point here. We always zoom on the right-hand side, so you will always see basically the roofline model with that kind of thing here, and it goes to actually the origin. And also, we are using logarithmic scales, so you just need to be aware of that. So very quickly, I will give you an example how we can basically do this computation by hand, like theoretically. So if you have matrix-matrix multiplication, that's kind of an easy example with a size of n for the matrices. So basically, how many operations do you have? You have 1 addition, 1 multiplication, but you do it n times n times n times, okay? So you have that number of addition, that number of multiplication, which gives you 2n cube, operations. And now what they are doing for the roofline model, and this is the tricky part, you want to maximize actually for a given application the arithmetic intensity. Because what you want to get with this roofline model at the end is your expected performance on a given application. And you want to see how far you are from this theoretical performance. So how to do that? The assumption that they are doing in the roofline model from Berkeley was that they say we have a perfect memory subsystem, meaning that if you reach one memory cell once, then every other access to this cell in memory will be for free. So you just need to pay an access basically once. And how do you do this here? Basically what we are doing, we count the number of reads and writes. So we have 1 write, 1, 2, 3 reads. And you might think that this is also n cubed, but actually it's not n cubed, it's n squared, because at the end what you are doing here is that you are reading all the elements of A, B, and C, and writing all the elements of C. But those matrices, they are in 2D, so that's n squared. So that's the reason why at the end you only have, so that's here, 16 n squared memory operations. Okay? Does it make sense? So you end up with this arithmetic intensity, n over 8. And this is actually one of the reasons why this test is so stupid to benchmark supercomputer. It's because the arithmetic intensity of LIMPAC depends on n, actually, the size of the matrices. So it means that if you have a very, very big matrix, then you will have arithmetic intensity so much on the right that it will be easy to be completely compute bound. And then you will be able to reach the maximum performance, which is probably not the case in real-world applications. So, I mean, we can try to ask you later during the break, but mainly the HPC application, you're memory bound, not compute bound. So what does it mean here? We have n/8 for the arithmetic intensity. How can you read that? It means that, for example, if you take n equal 8 for the size of the matrix, then you end up with an arithmetic intensity of 1, and you just report it on the roofline, and you read the performance here. And it means that no matter what you do, you can be a god of optimization, you can spend probably thousands of years on Ivy Bridge. There is no chance that you can optimize the matrix multiplication to better performance than 119 gigaflop per second, if your matrix has a size of 8. And this is really on Ivy Bridge, so you have both application and platform here on the roofline model. So that's very useful because then you can, with the roofline model, you can evaluate the theoretical performance for your application and check how far you are. So what you will basically observe if you try to run your application, you will see that your theoretical arithmetic intensity is, for example, here, but your point will be on the left-hand side, and you will probably not be that close to the roofline. And then you have two different strategies. So getting performance by vectorization or threading, you will just improve on the vertical axis. And then if you try to reduce or to optimize your memory access, you will change the arithmetic intensity. Then your point might move to the right, which will give you more headroom to get more performance. So the roofline model in Advisor is almost what I presented. I say almost because it didn't start like that. So the first implementation for technical reasons was what we call the cache-aware roofline model. And actually this version was based on instrumentation. So we took your binary, we ran your binary several times. A first run is done just to time your functions, so there is no overhead on this one. Then we have the instrumentation, so we count all the operations, all the memory transfers, all the trip counts and things like that. And for that, we are really counting what is executed. So this is not based on the assembly code that is generated by the compiler. We really intercept basically the binary and what is executed. So we really count the appropriate number of operations, for example. So there are some pros and cons for this version. So the first one is you might change your memory access. You will not see it most probably in this implementation, because we count at the assembly level at some point. So you will not see any difference, because if you need to access the data, you need to access it, basically. No matter if this data is already, you found a way to cache it in L3, L2, you will still see the same number of memory accesses. So the arithmetic intensity is not supposed to change here unless the compiler does some optimization. And so it's not easy to interpret, because at the end you have 1 point, you see the potential performance, how far you are, but you don't get any information how to move your point to the roofline, basically. But this is very useful to characterize your application. And actually last year we came, and that was still in beta since last year, we came with a new implementation which is called Integrated Roofline Model. The name might change actually in the future, but you will get the idea. So what we added in Advisor for this new version is a cache simulator. And we use the hardware configuration, so your hardware configuration, to set up this cache simulator. And then we can count how many misses you have, for example, between L1 and L2, between L2 and L3, L3 and DRAM. And then we end up with different arithmetic intensity based on different memory subsystems. And then you will see actually the points that can move on the horizontal axis. So it's much closer to the original implementation, or the original roofline model, the one from Berkeley that I introduced in the beginning. The bad news is you have the cache simulator, so it will take a little bit more time to run. But this is still manageable. You get something like 10x speed down or something like that. So of course you don't need to do it for every run. So that just to know where you are on your application, and then you're basically done. So just some additional information here. So I told you that arithmetic intensity, this is flops divided by bytes. And now we have different way to count the bytes. So we still have this way, the cache-aware roofline model, which is basically counting all the memory access from L1. So no matter where the data is, you assume that you will get it. So this is this first level, it's still available. Then you have the second level, which is counting the transaction between L1 and L2. And for those three last levels here, the way it works is a bit different from this one. For this one here, when you access the data, like a single precision, you will just count the size of your data, so 4 bytes basically. For those levels here, you need to replicate what the cache is doing, meaning that if you have a miss in L1, you will not count only 4 bytes that will move from L2 to L1, you will count that this is a whole cache line, so 64 bytes. Okay. So every time you have a miss here in L1, L2, or L3, you don't count just the miss for the data, you count the miss for the whole cache line. So 2 different ways of working between this one and those 3 here. But at the end, you end up with 4 different arithmetic intensity. So 4 dots basically on the loop line for a single loop in your application. So what can you expect out of this thing here? Well, so you can expect, if you are doing the thing right, if you are doing basically unit stride memory access, what you can expect is that arithmetic intensity of L1 will be lower than the one from L2, L3, and DRAM. And now I will try to explain why. And this is pretty important to what I will show you after that, because there is some demo and you need to understand this part. So that's probably the most difficult part of this presentation, I would say. So how does it work? You want to access data in an array, and then you start by accessing array of 0. So you have 2 cases. Array of 0 is already in L1, then you just count 32 bits from L1 to the registers. If array of 0 is not in L1, then it's maybe in L2, so you will count 64 bytes that goes between L2 and L1, and 32 bits that goes from L1 to register. So we have those 2, and we just try to count on the cache-aware roofline model size and L1, L2 here. And then same process would happen actually with L3 and DRAM. And then if we start iterating, what will happen? So you see that at this stage, actually, we transferred much more data between L1 and L2 than between L1 and the registers. So what I told you here is wrong. But if we iterate, then that will become actually true, at least equality. So if we iterate, then array of 0 was already in the cache, in the L1, because we maybe had the miss before. So if we take array of 1, then this is already in the cache. So we are not going to count any memory transfer between L1 and L2. We are just going to count 32 bits from L1 to register. And then that will be the same for array of 2, array of 3, and so on until you reach array of 15, which is still in the cache. So basically for all those accesses, you will not count any memory transaction between L1 and L2. You will just count 32 bits from L1 to register every time. So at the end, you will get exactly the same amount of data transferred for L1 and for L2. So that's how to explain the equality. And actually, in real life, you even have this inequality because in practice, you reuse data locally. So that's what you will observe in practice. But that will only work if you are using unit stride memory accesses. Okay, so that's how it looks like in Advisor. So this is a very simple application here. If you open the integrated roofline the first time on a real world application, you might be a little bit afraid because you will have points basically everywhere. But there is a system to filter the points, and then you can make it simpler. So how does it work? When you see that kind of picture, basically if the dot is big, it means that you are spending a lot of time in this loop. So each dot here is basically a loop. And all the dots on the same horizontal axis, this is the same loop, but for different memory levels. So for example, this one might be L1 for a given loop. For the same loop, that will be with data that comes from L2, L3, and DRAM here, okay? So you see basically those different dots here for the same loop. And how can you try to interpret then what you need to do? So for example, if I was starting on this application, I would probably start by trying to optimize this part here, this loop, because this is a big one and this is pretty far from the peak. So there is probably some easy gain to get here. And usually the higher you are, the more difficult it will be to get performance improvement. And those small dots here, it means that you are spending almost nothing, so you don't want to start doing optimization from here. So now I will just show you some demo how to apply those things here with the roofline model. I will also use actually VTune just a bit, but to give you an idea how you can do it on your applications basically. So I will use for that a code called ISO3DFD. This is a wave propagation kernel. So that's used in oil and gas, and this is based on finite differences. So we implement that kind of 3D cross that we move in the 3D volume basically. So if you look at what happened, so we have a 3D space. If you take some 2D slices, and you take it for different time steps, you will see that if we have a perturbation, basically we propagate it, and at some point here, you start seeing what we call reflections, and this is even bigger here. So that just to let you know that there is no boundary condition. So in a real code, we try to absorb those reflections. So usually we don't want those reflections to happen. But the idea here is to show some simple enough code so that we can move quickly and that's the main kernel. So this is what we are doing here, going through the 3D volume. So we have 3 for loops. And then here, this is the implementation of the 3D cross. So that's the stencil here. And then this is where we update the data. So this code, there is no MPI, it's just OpenMP, no boundary condition. So this is the 16th order in space. You can see it here because the half size of the stencil is 8. And second order in time. So what I did first was that I unoptimized this application to show you how you can basically check and move forward with Intel tools. So the first run that we are doing here, so I think if I recall it's on the Skylake system, 0.43 gigaflop per second, which is very low. And what I'm doing here is that I'm opening VTune, so I'm running a VTune analysis. Okay. That was open before, so probably it just crashed. Okay, it just crashed. So I will not show you VTune, but that's not a big deal. So basically what you will see if you run the hotspot analysis in VTune, you will see that you have just one thread that is used. So you have an histogram on the summary in VTune, and you have the thread histogram, and you will see that you are spending all your time on one single thread. So you basically want to optimize the threading to do some parallelization. And I can actually show you the initial code. Okay, so this is the one here. And you see that this is the main loop here. And on the second version, so what I'm doing here, so based on the results of VTune, I'm actually just adding a Pragma OpenMP parallel 4 on the first loop. And then that will parallelize at this level. And then when you run it, you get some speed up, which is basically 20x speed up. So, but this is not that amazing. So 20x speed up, I think that I had something like 56 cores in total. So we are still far from getting an optimal speed up here. So always try to put those numbers in relation with the hardware. When you see 200x speed up or 1000x speed up, it means that something is wrong. At least if no one explains what is going on here. So next version. So I'm getting this performance now, so 8 gigaflops. And at some point, I might be a little bit lost, not knowing where to go next. And this is where I'm going to use Advisor. So I already ran it. Otherwise, it takes some time, so I just want to show you the results. So when you open Advisor, then you end up in this summary here. So at this stage, you don't have a lot of very interesting information, except that you see that you are basically doing scalar operations, so you are not vectorized already. Then you have some information about the instruction set that is used. You have some information about the gigaflops that you are doing. So this is basically similar to the output that I get also in my application. And then you also have some information here about basically flops, bandwidth for the different cache levels here. So I'm not going to spend too much time here. I'm just going to show you the roofline model. So I'm switching here. You see you have some tabs. I'm switching to survey and roofline. And then I'm going here to roofline. And then this is basically the roofline model in Advisor. So you see that you have basically 3 different sections. So I don't know if you see it clearly, but you have a first left-hand side here, which is memory bound. You have something in the middle, which is in between, and you have the compute bound part on the right-hand side. So you can actually make it a bit simpler by playing with those things here. So for example, this is single precision here. So I can remove all the roofs for double precision, and I can just keep the one for single precision. And also, I'm not really interested into the add peak, and I will use the FMA peak, which is basically the highest one. Okay. And then what you can do here, you can move to this part here, and you can enable the different dots, so the different memory subsystems. So, and that's what I was mentioning in the first place. So initially, this is the cache-aware roofline model. If you just have one dot, this is cache-aware roofline model. But the problem is that you don't have any information. You don't know if this performance, you are far from the roof because you have some memory issue, because you are not vectorized, because many things, you don't know it. And so that's the reason why here I will just enable the different memory hierarchies. Okay, and so what we can see here, so this loop here end up now with 4 different dots. I will just zoom here. And now when I just display where those data come from, you see that my first dot here, this is L2, then this is L1, L3 DRAM. I told you that you should always see L1 before L2 if you are doing unit stride memory access. If you see this kind of weird order here, it means that you have some memory issue in your application. You are not accessing the data basically with unit stride memory access. So if you want some details about what is happening, for example, if I'm doing random memory accesses, so I will count basically only the data that I'm really accessing in the L1 here, like 32 bits every time. But for the L2, because the data will not be in cache, for every access, I will need to transfer between L2 and L1 64 bytes. So it means that for this one, only 32 bits for each access, and this one is mainly 64 bytes for each memory access. So that's the reason why the arithmetic intensity here is lower. So we need to basically check what is happening. So when as I'm selecting this, so I can go actually in the code, that will be simpler. So I need to understand at this stage what I'm doing wrong. So basically, I need to just understand how I'm accessing the data here. So I have only very few variables, very few arrays. So it's not that difficult in this case. So I have value. Value is just a local variable, so there is no chance that my memory access are in pain because of value. Same for offset here. This is actually what I'm using to access data later. So I have another array which is called coef. And if you look at the code, coef has very few elements, so just 8 different elements here. So it's not the reason for my problems. So the only one that has some kind of dynamic addressing is this one. So ptrpref and also, no, that's it. And then you have also those arrays here. So you need to understand how we access ptrpref. So we use offset. Offset is here. And what we need to try to ensure is that for every new iteration, so on the last level here, we are going to increment this one by one. And what is going to happen? So actually, if the last level is IZ, we are going to increment by the 2 first dimension every time. So we are doing a huge jump in memory. If the last level is IY, then we are going to jump by the first dimension. And if the last level is IX, then we are going to do unit stride. If we increment this one, and actually when you look at here, our innermost loop is IZ. So the loop order is wrong here. So basically what you need to do is take this loop at least and put it here to ensure that you are just doing unit strides memory accesses. So it might look actually stupid. You might think that, okay, I'm not doing that in my code. But this is something that I already observed on real customer codes. For one reason mainly, it's basically when people move code from Fortran to C or C++. Because the way of iterating is basically the opposite. So you can see those stuff in real code actually. Okay, so if you do this optimization, you just change the order, then you get a 3.3x speedup. So you go from 8 gigaflop to 26 or 27 gigaflop. So what's next? Again, you might be a little bit lost, so you can still run another time advisor on your new version. So this is what I'm doing here. And again, you see here in the summary that you have some Scala time, so basically not vectorized. So you can go to the survey here. I'm not going to open the roofline this time, just the survey. So this is a very short analysis to run. And I'm just going to look at what seems to be the problem. So I have here in this section, advisor tells me that this loop is scalar. So that's my main hotspot, by the way. This is ranked by self-time, so this is my main hotspot. And it tells me that this is a scalar loop, so no vectorization. And it tells me that the outer loop was not auto-vectorized. Consider using SIMD directives. So when I can switch on those tabs here, so for a given loop. And when I go to why no vectorization, then I have some explanation, so you can read it. Sorry that we don't have the time for that today, so you will have to trust me. And basically, it will tell you what you can use. So Pragma, OMP, SIMD, for example. And it also tells you actually which line here. So you see basically which loop is impacted here. So that's just following advisor's recommendation. And I'm just adding this line, this Pragma, OpenMP, SIMD. So just before we do that, actually. So when you force vectorization, there is a chance to break your results. So if you have data dependency, you can't put vectorization everywhere. You need to check that vectorization is safe. An advisor has a test for that. So actually, if you read it carefully, they will tell you, probably somewhere, that you can run. So I don't know where it is, but this is here. They will tell you you should run the dependency analysis if you are not sure that you can do the vectorization. And we have a test called dependency analysis. So how to do that? You just basically check your loop here, and you run collect on dependency here. It will run a test that will take a lot of time, that will check all your memory accesses, and at the end, it will tell you if there was some dependency or not in your run. And so here, when you do it, it tells you no dependency found, so you are safe to do the vectorization. So just a warning, I'm always giving this warning for this dependency analysis. So if it tells you that you have no dependency, the words are very important. It's no dependencies found. It doesn't mean that you don't have dependency. It means that for the run that you did, with the parameters that you use for your application and everything, advisor didn't find any dependency. But it might be the case where changing your parameters for your application might read, I don't know, a file or something that will change basically the size of some padding in your code, and then you might have some dependency. So you always need to be sure when you force vectorization that you are not going to break the result. So this is up to the developers. That's not basically up to advisor to. So the idea is that if you fail your code or you crash something, or I'm not responsible for that. So that's basically the idea. Okay, so here this is safe. We can vectorize. So I'm just following advisor's recommendation, and I can show you here. So, no, this is already the next version. Yeah, this is the one here. So I'm just adding this pragma open MPCMD, and then I'm running it again. So when you enable vectorization here, you get 1.5x speed up. So this is almost a bad news, actually. So you might be happy because you get some speed up, but this is not that interesting here. And the main reason is probably because I have some memory issue again. So why is it not interesting? So I'm using AVX2, so which means that on single precision, I could expect something like 8x improvement due to vectorization. And I'm just getting 1.5. And it means that there is another issue with this code, and I need to find out what is the problem. So I'm taking this code again, and I'm running advisor because I'm out of IDs. So this is the one here, I guess. Yeah. So we have enabled vectorization. You can see it here. So it tells you that basically you have some time on vectorized loops. And then I'm going to the roofline model here. So I will zoom a little bit. And I'm going to enable the integrated roofline model. Okay. And then I'm going to actually zoom here. So my main hotspot is this one here. Okay. So what can I do now? And how can I read it? So actually you can see that the order is good now. So we have the L1, L2, L3, and the DRAM. So at least we are doing units right. So I need now to actually do some projection. So to check where my performance, or what is my theoretical performance based on a given memory subsystem. So when I'm taking the L1 dot, I need to project this dot on the L1. So actually L1 is here. So we are under compute bound section. So I will need to project it here. For the L2, I will need to project L2 on the L2 bandwidth here. So that's the different bandwidth that you have. So that's L3, L2, and L1 here. Same for L3 and same for DRAM. So when I do the projection on L1, it tells me that I have potentially almost 40x improvement possible, and I'm far from it. So it means that I'm not limited by the L1 speed so far. I'm so far from it that this is not my main issue so far. So for the L2, if I'm able to get data completely from L2, I should get 27x speed up. So again, I'm very far from it. This is not what is limiting my performance so far. For L3, 18.4x potential speed up, so again, very far from it. And now for DRAM, you see that in the best scenario, if I'm not changing a lot of things, and if I'm just able to get as much as possible and as fast as possible the data from the DRAM, I can just get a 2x speed up. So it means that I'm already hitting the DRAM roofline. And I need to find a way to reduce the data that I'm using or I'm reading from the DRAM. So it means that if I want to get some performance now, I need to find a way to take this point and put it here. So I asked actually advise our development team to implement something where you just drag and drop the point and you change the code. But it's not working that way, apparently. So what I'm doing now is implementing something called the cache blocking. So cache blocking, the idea is instead of iterating on the whole 3D problem, I'm just creating some blocks. And by creating some blocks, you basically get more data locality and you reuse much more data from your cache. And I'm trying to manage the size of those blocks so that the data will fit in L3, basically. That's the idea behind. So I will show you the implementation. But when I'm doing this, then I get a 2x speed up, so 2x additional speed up. And if you look at Advisor, after this version, sorry, this is here. So this is what we have now, and I will just use the compare feature of Advisor to compare it with the version before cache blocking. And so the version before cache blocking, this is the squares here. And my version with cache blocking, this is the dots here. And remember what I told you. I told you ideally what I would like on this version was to take this one here, to move it on the right, so that I will get some headroom. And this is exactly actually what is happening when you implement the cache blocking. You just take one given dot, or two depending on the size that you are using for the cache blocking. You're moving this point to the right, and then you can get more performance. So just to conclude, I can show you the code very quickly. So cache blocking, this is pretty heavy. Okay, so this is how we are doing it. So we had 3 for loops in the first implementation, and for each for loop we create an additional for loop. And then we create blocks. So this is what is done here on the first 3 for loops. So the parallelization is done on those loops. And instead of incrementing by 1, we increment by the size of the blocks here. And then you just need to propagate the boundaries into the original for loops. So that's basically how it works. It's not a big deal. You can do it with a lot of mistakes by doing copy-paste. So usually you spend some time debugging that kind of implementation. But this is not very difficult to implement. You just need to understand how it works. So just to conclude, I could actually get better performance just by doing something here. Just by exporting actually KMP affinity scatter, because I was on a system with hyperthreading on, and hyperthreading is usually not that useful for HPC application. So I'm actually just using as many threads as I have of physical core, and by using scatter, I'm ensuring that I'm just using each core separately. And then you get a little, say, boost. And you could actually get another boost here by doing something called first touch policy. So making sure that you don't have NUMA effect. So this is something that is kind of painful for this code. The fact that basically I'm not taking care of splitting the data across the 2 sockets. And I'm reading all the data from a single socket. So this is due to the fact that I'm using a 2-socket system here. But and for that you can use actually VTune to track it down. So that's it for this presentation. I hope it was useful. So you can see that it's not that difficult to use Advisor. So most of the things that I showed you will be, you will have automatic recommendation in the future. So this is still in beta, and we expect to have those recommendations probably for next year, but you can already play with this tool already. So thank you for your attention.
Last one before the break. Stay with us. So this is, if you look at the agenda, this is going to be a packed session all around floating point reproducibility issues. I think you guys are pretty much aware of that kind of issues. Probably you should make now floating point reproducibility issues. That's the first track of a long series. So stay with us until this early autumn. And then get into really deep performance, and we should wrap up the session with the automatic joint differentiation solver, which should also give you some nightmares. Lovely. Also,
Thank you. So can you hear me? Okay. Well, thank you for being here, and thank you for attending this. I'm going to talk about debugging floating point related issues. My name is François Févrot, and I'm working for a new company that's called Prescale Innov. And most of what I'm going to be presenting is a joint work with my former colleague Bruno Latuyère, who is still working at EDF. Before I delve into more details about floating point related issues, I wanted to tell a few words about who we are at Prescale Innov. And I think our main idea is that in most projects where you deal with technical and scientific computing, you really would like to have more tightly integrated work between the different areas of expertise that are involved. And usually, I mean, most projects that we have seen so far, applied math come before software development, which comes before hardware architectures considerations, and most projects, in our opinion, will benefit from a more tight integration between these areas. And it's in this spirit that we provide services such as professional training and consulting and software development, trying to bring all of these together. And I think this topic that I'm going to talk about, numerical quality, is actually a very good example to illustrate this. Because if you look at what happens, for example, in terms of verification and validation of numerical software, I mean, the whole process looks like this. You take something that you want to simulate in real life, maybe a nuclear reactor, maybe a financial market, and you model it with mathematical equations, and then you devise algorithms that you implement, and then your implementation is going to run on some hardware, ultimately giving you some results that hopefully represent something on your real system. And if you look at all these stages, each one of them introduces some errors. And the process of verification and validation consists in trying to analyze these errors. And if you look at these specific errors that are, sort of due to the fact that your hardware is running on floating point arithmetic, whereas your algorithms and your mathematical models usually are thought about in an ideal mathematical world where all numbers are real. I mean, in this instance, you see that there's kind of discrepancy between how you think about your algorithms and how these will be implemented and run. And this is typically a case where you want to have this integrated view. What's at stake here is, of course, the quality of the results, the reproducibility of your results, the accuracy of your results. But more and more, what we observe is that what's really at stake is the time you spend trying to debug these issues, trying to develop your code, and also the time you spend computing. We all, I think, are aware that it's easier and faster to compute with smaller numbers. And if you can have the same accuracy with floating point 16 bits, then maybe you'd like to have that. I'm not going to enter too much the details about floating point representation and all else that are due to that. Just a few words to remind you about I think the main four types of errors that you can get. When we think about round-off errors, what we think about is, round-offs, okay? You have an operation, say an addition, maybe a multiplication, and I mean, you have two operands, and the result does have some digits that you don't have enough space to store. And so you have to round this result off. Okay, this is what you think about, and this is not the worst thing that can happen, because these errors are bounded by what's called the machine epsilon something, in something like 10 to the minus 16th in level precision. So, I mean, this happens, and this is not the worst case. Something that we mostly think about when using numbers like pi, is that some of the numbers cannot be represented in a finite sequence of digits. Of course, we think about it for pi. Maybe we don't think too much about it for numbers such as 1/10, which is easily represented in radix 10, but as a binary, in a binary representation, it does feature an infinite sequence of cyclic bits. But anyways, these errors are also bounded by machine epsilon. What's worse is cases where your errors are amplified by some things, like cancellations, where you subtract two numbers that are so close to one another that the result is many orders of magnitude smaller than the operands. And in this case, what happens is that you do have some space to store additional digits, but you don't know what to put in there. And in this case, I mean, what should be in there, you really don't know. This should come from some bits, some digits that you lost somewhere in the process before. And in these cases, the error is not bound at all. I mean, you could even not know the sign of this number, the resulting number. Another case that might be even worse is when you have a test and the branch that you take depends on the comparison of two numbers that are so close that you don't know which branch to take, and the decision is made using essentially nodes. Okay, so these are maybe the two that you want to be really well aware of. During the presentation, I'm going to have this example of a real-world application where we used some tooling in order to understand what happened in this code, which is a numerical platform for the simulation of mechanics. It's kind of a real-world code with more than 1 million lines of code in a few different languages with a lot of third-party dependencies. And they have this really nice continuous integration test suite with a lot of test cases, and they being the development team of this code, they observed that in some cases, in some instances, some of the test cases would yield different results on different test machines. And they wanted to try and understand what happened, whether it was related to floating point issues, which tends to be the immediate culprit that we think about in these cases. And they wanted to fix bugs or understand whether these were bugs at all. If we look at such a case and we try and imagine an ideal tool that would allow us to analyze such things, we can try and have a three-stage process where in the first stage, you really want to just get reassured that the abnormal behavior that you observe is really related to floating point issues. It might be related to something else, but if it's related to floating point, then you know you have to look at certain things and you want to know beforehand whether this is the case. And if it is, then maybe you want to understand the magnitude of the effect that round-off errors might have on your results. In a second stage, you want to try and debug your code, and this involves knowing how the code you write relates to the behavior that you observe. This relation between the code and the behavior can be both either what I call spatial, which is maybe the bad behavior is caused by some functions or some lines of code that you have written, or maybe it's more temporal, meaning that errors come from the early iterations or late iterations, or maybe from a function, but only in a specific context. And then in a third stage, maybe you've got a very stable code and you want to try and shrink the numbers as much as you can to have like 16 bits floating point numbers and use mixed precision arithmetic where needed to have the best performance. The tool I'm going to talk about is Veru. It does not have all these features, but it does have some of them. I developed it back when I was working at EDF with Bruno Latulière. It's open source, you can download it from GitHub. And so, yeah, let's just look at how it works. So the basic idea is that if you run a code under IEEE 754 like standard mode, standard arithmetic, what happens is that when you execute some instruction that has an inexact result, this result gets rounded to one of the nearest two floating points. By default, it's the nearest one. In this case, it's 0.333. There are some alternate arithmetics that we can use, and one of them is called stochastic arithmetic. And in this case, what you do is just each time you have an inexact result, you flip a coin and either round down or up. But this is stochastic. Each time you have one instruction in your code, you repeat the process, and some of them will be rounded down, some of them will be rounded up. Essentially, when doing this, you're turning each single operation in your code into a stochastic operation, and you're turning your whole code into something that looks like a Galton board, where the first result is going to be, your first intermediate result is either rounded down or up, and it's going to be used as an operand for the next operation, which itself will be rounded down or up. In the end, you're turning your result, your whole code result, into a realization of a random variable, and if you look at the dispersion of this random variable, you can have some insight about how round-offs affected your outcome. So this is what I'll be calling a backend. So it's something that you can use as a drop-in replacement for standard arithmetic. And in order to implement this, you need to have something that's called a front end, which will be something that takes your code and replaces all arithmetic operations with this alternate version of the arithmetic. And in Veru, what we use is valgrind, and this means that you can take your code as it is and compile like usual, and you have this valgrind layer that interfaces between your binary and the real processor, and this one is in charge of replacing all arithmetic operations with the alternate versions provided by the backend. So maybe just a very quick demo. If I take my favorite binary, which is, for example, Python, it allows me to do almost any calculation that I want, and I don't have to recompile Python with all its dependencies. And of course, if I execute some Python code and run 3 times the same computation, I will get 3 times the same results, because this is IEEE arithmetic, and this is what we love about it. It might not be 100% correct, it always gives the same thing. Okay, now if I want to run the same Python interpreter within the Veru context, what I just need to do is prefix the command with an invocation of valgrind and the correct switches. And what happens is that I have a small header that tells me that Veru is running, and it's instrumenting all these kinds of operations. And now, if I run the same calculation, I get a result that's not exactly the same as what I had before. But more importantly, if I run 3 times the same computation, I get 3 different results. And I see that all these results have the same first 13 numbers, but then the last 3 or 4 ones are changing from one run to the other. And this means that perhaps round-off errors, in this case, well, have an impact on only, I mean, an impact in the order of magnitude of 10 to the minus 13. Okay. So if we go back to our industrial test case, where we had this big mechanics code, code Aster, and we look at what happens. Okay, how does it look like in real life? These are a few test cases extracted from the suite of code Aster, and of course, if we run them in IEEE mode, all of them pass. Okay, we can run them in random rounding mode using Veru, and all we have to do in order to do this is just prefix each invocation of the test suite with the invocation of Veru. And what we see is that most of the test cases seem to still pass, but this one does not. Okay, everything is random in this column, so maybe, I mean, maybe these pass by sheer luck, and maybe this is just bad luck. So we can perform a few experiments like this, and it does look like, okay, these 8 cases are more stable than this one. In order to reach this conclusion, I mean, you spend something like an afternoon introducing some new commands in your test suite and running it a few times, okay? If you want to go a bit further, you can extract the numeric results from your test cases and look at how many digits they have in common. And then it tells you that, okay, all these test cases do have a lot of numbers in common, and maybe having 10 numbers in common for a mechanics application is enough. And this failing test case features differences from run to run in the order of 10 to the minus 3. So this might be not what you want. Now, if you want to go one step further and try and debug, a third thing that you might want to be aware of is whether you do have unstable branches, which means tests whose outcome depends on floating point issues. And one way of doing that is to sort of hijack coverage analysis tools. So if you perform some coverage analysis of code Aster, what you get is something like this, where you see that we hit this line 120 times, and the partition is 13 times this branch and 107 times the other branch. If you run the same test under Veru using stochastic arithmetic, what you see is that you hit the test the same number of times, but these are partitioned a bit differently. And for example, this branch has been taken 4 times instead of 13. What this means is that this test is unstable. Depending whether round-off errors occur before it happens, the outcome of the test is not the same. And this gives us some insight that maybe this whole formula that's implemented is not correct. I'm not going to enter the details of how we could correct it, but we can. It's just a matter of implementing a good formula that's mathematically correct while being also correct under floating point arithmetic. A second way you can try and debug your code is using something that's called delta debugging. That's been invented by Andreas Zeller in 1999. And it relies on the ability that the front end has to instrument only part of the source code. You can run only part of your code within Veru, which means you can instrument none of the functions, in which case you should have a passing text. You can also instrument all of the functions, and we have already seen that in this case the test fails. But you can also decide to only instrument the first half of your functions and look at what happens. Okay, and if you proceed like this in sort of a bisecting manner, what you end up doing is you have a list of all functions that are deemed unstable in the sense that if you perturb all other functions except these ones, the test will be passing, and if you perturb one of these in addition to the others, then that makes the test fail. And all this can be automated provided that you provide some script that tells Veru how to run your test case. And you also tell it how to validate that an output is correct or not. Okay, this can be performed either at the level of functions or the level of source code lines. If we run this on Codaster, what we end up with is, for example, this function where we have 3 lines deemed unstable, and if we had time to look at them more closely, we'd see that these pretty much look like some form of scalar product. Okay, we have accumulation variables here, in which we accumulate the same value plus the product between 2 things. Okay, so this is actually a matrix vector multiplication, and the standard solution to such things might lie in compensated summation algorithms or dot product algorithms. And if we implement, for example, the algorithms that are introduced in these papers, you actually fix this issue in Codaster. Okay, third stage of the analysis. If you get to a point where your application is stable enough, you might want to analyze which part of the source code can be downgraded to lower precision. And in order to do that, we have an alternate backend that instead of rounding randomly, what it does is it takes a high precision value and it rounds it to low precision before performing all operations. And this means that you can emulate the use of a lower precision arithmetic than what you have compiled your code for. But of course, you won't have the performance boost yet. Okay? It's just to help during the analysis phase and help you determine whether one part of the code might be using safely smaller floating point numbers. Currently, we only have one implementation for double to single precision, but we could have very easily all other reductions. But we can't, for memory issues, we can't take a single precision and emulate what would happen if it had been a double precision number. Okay? So we can only emulate a reduction in floating point size. And of course, this is a backend, and it can be combined with everything that we've seen before, like delta debugging or code coverage analysis, which means that it can allow you to automatically determine which parts of the source code would yield unacceptable results if they were to be using lower precision numbers. Okay, so if I want to wrap up everything that I've said, Veru can help you diagnose whether the bad behavior that you observe is related to floating point issues, especially thanks to its random rounding backend. If you're willing to perform a bit of post-processing, you can quantify the magnitude of the errors that you have. As far as debugging is concerned, we do have a lot of options to perform what I call the spatial analysis. That is to say, locate which parts of your source code, which functions, which lines produce errors, but we do not have yet much that helps localizing in space, in time, which parts of your computation are producing errors, whether these errors come from the early iterations or last iterations. As far as optimization is concerned, we do have this reduced precision backend, and it works. We just don't have much experience with it yet. So, I mean, this is mostly future work. Maybe you'll hear from this again in one of the later talks. So as you see, Veru does have a few, I think, useful features. It's still no silver bullet, and I think we would all benefit from having, I mean, more techniques, more tools. And this is why we've tried in the past few years to build this consortium, which is called Interflop. It's pretty much essentially French up to now, but hopefully we'll have a more international consortium in the future. And this is both a sort of toolbox where we try and isolate as many building blocks as we can in a way that's as interoperable as possible, so that we share much of the development. And it's also a broader consortium where we try and share research. And essentially, we're interested in exploring how stochastic arithmetic, which is very well suited to the analysis of industrial codes, can complement an analysis that would be performed in a much smaller scale using techniques such as interval arithmetic, which is very well suited to a smaller code. So as I said, we have a lot of partners, but they are, I mean, most of the people involved are in France. This concludes my talk. And so if you want to use Veru, again, you can go fetch it from GitHub.
Can I ask a question?
Yes, please.
Very interesting talk, thank you. The stochastic arithmetic that you use, of course, is presumably quite expensive because you're checking random numbers all the time.
Mm-hmm.
Would there be any benefit just to changing the IEEE rounding mode so that it, for example, always rounds to plus infinity or minus infinity, which is kind of analogous to always going in the same direction with the randomness?
Yes.
Or does that completely break all the things you're trying to do?
No, it's a very good idea, and actually we do have backends that always round down, always round up. And I mean, what can I say? In theory, it's better to have a random rounding, but in practice, you get almost all the benefits of the analysis with simpler rounding modes like directed roundings. So one of the very pragmatic things to do would be to run your code like maybe not 3 times in random rounding mode, but maybe 4 times or 3 times. 1 time using rounding to nearest, 1 time using rounding downwards, 1 time upwards, maybe 1 time towards 0, and then you have a panel of results, and this already gives you, in a very deterministic way, quite a few results. And you can do this with Liam if you want.
Sorry, how do you get access to the binary page?
Okay.
Is it on binary level, or is it on assembly level, or is it on function level?
Okay, the thing is, we really don't want to do this by ourselves, and this is the reason why we use Valgrind, and that's actually what Valgrind does. I mean, we all maybe know Valgrind for its memory analysis tools, but what it is really is a platform that allows one to develop such tools, and what the platform does is it deconstructs a binary. It represents it in some sort of intermediate representation, much like LLVM does, except it's not the same IR, but it's same kind of techniques. And what tools like Veru or Memcheck or whatever tool, Valgrind-based tool that you might want to use, what these tools do is they take the IR and they translate it to another IR and give it back to Valgrind, which then recompiles it and runs on the machine.
And Valgrind can work with any binary. It doesn't require to compile to
Yes, it can work with any binary. It does not work on every platform though. So currently it's restricted to Linux and Mac OS. And Valgrind can take advantage of dwarf information so that if you compile your binary with debug information, then you can have more insight of where things happen. But it does work if you don't have these dwarf information, it just isn't as helpful. Okay. Time for a break. Okay.
I think the mic's working now, yes. Hello everybody, my name's Mick, I work for the Numerical Algorithms Group, and today I'll tell you a little bit about NAG for people who don't know us and what we do, but then more importantly I want to talk about software reproducibility and the tools that we have, and some good news from the Intel compiler folks that helps us with what we want to do. So, for people that don't know NAG at all, well, one of our oldest products and most ongoing products is the NAG library. It's a general purpose maths and statistical subroutine library, and it contains lots of different algorithms and methods for all sorts of things. Some of the important things I would say are optimization, so mathematical optimization, minimizing and maximizing mathematical functions. We also have lots of data fitting and differential equations, special functions, statistical analysis, things like k-means clustering, regression, and so on and so forth. We've got different variants of the NAG libraries. Some of them they contain all NAG code. Some of them are based on things like Intel's math kernel library, MKL. And all of this stuff is callable from lots of different environments or programming languages. So traditionally, we had people working in Fortran and older style languages, but also C and C++ and Python and MATLAB and Java and all of these things are all possible. So our customer base is pretty widespread. We cover all sorts of science and engineering. And one of our most important customer sectors is, of course, finance. So for people that do know the NAG library, you may remember that we used to have different variants of it. We had what we call the NAG Fortran library, where all the routines were written in Fortran, callable from that language. We had a NAG C library, which was usable for C and C++. Both of these libraries could be called from different languages, like MATLAB and Python and .NET and so on. What we've done at the very latest version of the NAG library, which is Mark 27, we've merged those interfaces into one library. So one library now contains all the C and the Fortran interfaces, and again, they're still all callable from all these different languages. So product code, for people that are familiar with the old NAG library product codes, they used to begin with FL and CL for Fortran library and C library. Now we just call it NL for the NAG library. So you can use that as a drop-in replacement for any of the old Fortran or C libraries. The other thing that we've done here is merge together 32-bit and 64-bit integer versions of the same library, because some people need to use 64-bit integers, some are happy with 32 bit. So it's all in one product now, makes it easier to decide what you need. So it was a large amount of effort on our part to do this merging, but the advantages are that you don't need to know in advance what you're going to be using or what you need to use. Python variant of the NAG library is becoming really popular, and that's available at the same time as the regular libraries as well. One thing that some people have been asking for a long time from NAG is, although we had the old C library interfaces, which were perfectly callable from C++, people were always asking us for specific C++ interfaces to make it easier to do things like object-oriented programming, where, for example, you might have a member function that you want to use as the objective function for a minimization problem. So we've recently been doing a lot of work to help along those lines. We're introducing real, genuine or proper C++ wrappers or interfaces to the NAG library code. So that should make it easier for people in the future. It's pretty flexible because for storing arrays or matrices, we cater for all sorts of different array type arguments using templates. So we support standard vectors and boost matrices, and it's fairly easy to modify this stuff so that it will work with any kind of array templates or containers. I/O is all done via streams, so it's easy to change that. And error handling is all done via exceptions instead of the traditional way that we did it in the NAG library, which was to return failure codes and error message strings. So it's all done by exceptions now, so you can do proper try and catch exception handling in C++ code. So some of the highlights of the latest version of the NAG library these are selected highlights, there's a lot of other stuff as well, but things that I thought you might be interested in are the optimization methods. The second order conic programming we've got a new solver in there. We've got first order active set methods, again for nonlinear programming, large scale nonlinear programming problems. Derivative free optimization, no need to calculate derivatives or estimate derivatives. We've got lots of AD-enabled code in the NAG library now, so this is a project that we've been working on for quite a while. People that need to use algorithmic differentiation, they need the NAG library to be aware of that AD, so that the entire computer program can be differentiated. If the NAG library didn't deal with it, then it would mean that they couldn't use the NAG library in the higher level AD-enabled codes. So that's something that we're vastly expanding in the future. It's expanded at Mark 27, and we'll be getting a lot more in the future. Various other things. So a new chapter for randomized numerical linear algebra, and various other things. So I wanted to move on to reproducibility of results, which is the main focus of what I'm talking about today. Lots of people need to generate results that are reproducible, and we've already heard a little bit about it this morning. We'll be hearing more about it, I think, today as well. So problems that make this difficult are that computers have finite precision, as we saw in Francois' talk this morning. The IEEE standard for floating point arithmetic does help, but it doesn't take away the problem entirely. And that's because we rely on things like vectorized register arithmetic, so SIMD arithmetic, and so on. Usually, when you run your program, if you're running it in different environments or even the same environment, the differences are very small and don't really matter. But sometimes those small differences can get magnified into larger differences, and I'll show you an example of that in a short while. And also, even the small differences might be very important. If you want to be able to run a test program and verify very quickly that there is nothing changed in your program, you want to see the exact same results. You don't want to see even tiny differences. So just a reminder what SIMD instructions are: single instruction, multiple data. These are things that let you store multiple numbers in one register, and then you can operate on all those values at the same time. So here I've got a register that contains 4 numbers in it, 4 floating point numbers. I've got another register with 4 floating point numbers. One instruction will add all of those things together. So gives the potential for running your code 4 times as fast in any way that's using these instructions. So normally, at night, when we have lots of test programs, obviously, for all our different algorithms, and we don't normally expect to get identical results across all different kinds of hardware. So our test programs are written with tolerances in there so that we accept that small differences will happen. But sometimes it's possible for, because of using these SIMD instructions, or for other reasons as well, but I'm talking particularly about the SIMD instructions today. Sometimes it's possible that you can run the same program with the same data on the same machine, and 2 consecutive runs will give different results. Now that is very, very disconcerting, and sometimes those different results are not just slightly different, they can be completely different. For example, doing a local minimization problem where you've got a function with multiple minimum values. If you've got a small difference that appears somewhere while you're searching your search space for the minimum of your function, it's possible that you will go down one direction and find one minimum. It's possible you might find another minimum. That exact scenario happened to one NAG customer who reported it to us. And he said, look, I run this program 10 times in a row. 8 times I get one minimum comes back, but twice I get this other minimum. And that's on the same machine, same data, running the same executable. So he was a pretty smart guy and figured out what the problem was, and it did turn out to be these SIMD instructions. So yeah, NAG customers do notice. We do try to, in NAG documentation, we tell people why reproducibility is a difficult thing, and it's good if they don't rely on getting exact results at the same time. But still people do want these things, so we do need to cater for that. Just one issue with numerical computation that I came across not so long ago. This is a little bit of Fortran code here, and it's very trivial code actually. It just declares 3 arrays, 3 vectors, f, g, and h, and I give it a value of n, which says how long I want the vector to be, and then I set all the elements of the first 2 vectors to equal to exactly 1.0, and then I do a division, so I calculate the elements of the 3rd vector are just the 1st vector divided by the 2nd vector. Now, obviously, you'd expect the answers to be 1.0, and I print these things out. So look what happens when I run that, if you can see these numbers. This is what I got. So I'm using the Intel compiler. The program's called test.f90, so I compile it with no flags, and I run it. And this is what happens. I gave it the value 5, so my vectors are of length 5. Here's my first vector is all 1s, my second vector is all 1s. My result vector, which is the first divided by the second, gives something odd. 0.999999, 0.9999, so 4 lots of 0.999, and then the 5th one is 1.0. Well, how can that be? Well, some investigation using the debugger and stepping through the assembly code that the compiler had generated showed me what was happening here. So instead of using divide instructions to divide these numbers, it was using an approximate reciprocation instruction, which took the divisor, that's these numbers, these 1.0s here, calculated an approximate reciprocal using a SIMD register, so it's fast. The approximate reciprocal is only accurate to about 3 decimal places. And then it did a Newton iteration, one step of a Newton iteration to refine that result. And because there was only one step there, a Newton iteration, you expect to double the accuracy of your result. And it just about did, but not quite. So you ended up with a number which wasn't exactly 1. And then you multiplied that by the numerator, and you end up with this number here. So it looks kind of odd. Some of these things come out as 1, and some of them come out as 0.99. Why does that one come out as 1? Well, it's because the SIMD register length is 4. So there was an odd one over, and that one was calculated using a proper division instruction instead of the reciprocation. So it's slightly disconcerting when things like that happen. But the reason it happens is because the compiler's generated code which is a little bit faster than you would have got if you used proper division instructions. Right, so a little case study. This is something that one of my colleagues was working on a few weeks ago. And he's been writing some code to simulate stochastic volatility. And the way he's doing that is using a stochastic differential equation, which is this thing here. So you won't be able to read that from very far away. It doesn't really matter. We've got volatility at time t, we've got the mean reversion rate, and we've got variance in the volatility of the volatility. Now, he was using a scheme that discretized this SDE, this stochastic differential equation, in time, and then solving it, getting an approximate result using a Monte Carlo method. And what he observed was that he's using the method that he used to solve this thing is called Euler FT. I don't know what FT stands for, I think I did once. Anyway, so he was wanting to know what was happening. So he struggled with this thing, and he came to me about 3 weeks ago and said, look, I've got this code, and I run it on one machine, and my calculated option price is this thing, and then I run it on another machine, and my option price is this thing. So they only agreed to 3 decimal places, and this is all using double precision arithmetic. So I talked to him for a while, and we tried it on a few other machines, and we found that they always fell into these two camps. Sometimes they were this first value, and sometimes they were the second value. So not very good getting 3 decimal places accuracy on a double precision code. I looked at these different machines, and I realized that some of the machines had AVX capability, the SIMD instructions, and some of them didn't have AVX, and that seemed to be the split. So I thought, well, it's probably because of the use of these SIMD registers, these AVX registers. So we compiled the code, the whole code, not to use AVX registers at all, and I thought I was very confident that that was going to fix the problem, and you'd always get the same results. Well, that didn't work. So Philip is the name of the guy that brought this code to me. He'd already tried a lot of things trying to fathom out why these differences were happening. So we did a bit more, and we put lots of print statements in. Using debuggers wasn't much help, actually, because they had massive arrays of things that you couldn't examine very easily. We put print statements in and tried to track down where this iterative algorithm, this Euler FT method, was diverging. And it turned out that the first difference turned up in a call of the elementary function exp, the exponential function. And it turns out that these machines we've been testing on, they all had slightly different versions of the libm library, the low-level math library. And the differences that were coming out of the X function were tiny. It was one bit different right at the very end. And only for very few arguments, actually. But it turns out that the Euler FT, this iterative solver scheme, magnified these differences until they were very large. And I don't know why, and I think the tool that Francois was describing this morning might be very helpful to us in doing this. And I'm going to suggest to my colleague Philip when I get back that we should try that. But anyway, as a pragmatic solution, what we did, we just inserted our own version of the exp function in there so that we're not relying on the runtime library exponential function. It turns out when we do that, all the machines we now test on, they always get the same results. It turns out they're not equal to either of the original set of results. They're somewhere in between, but at least now they're consistent. Now, that's all very well. It probably means that the Euler FT method is not stable at all. And that's what we want to investigate. And, there are other methods for solving this problem, and there's one called Anderson QE, and it's more accurate, it's more time-consuming, takes longer to do things, but it's a better way of doing it than using the Euler FT method. So Philip's writing a technical report about all this thing to help us in future to avoid this kind of problem. Right, I'm just checking how I'm doing for time. Right, so our customers want us to use SIMD instructions like AVX. Why do they want that? Because it generally can produce faster code, so they obviously want that. On the other hand, they don't want non-reproducible results. They want their test programs to get the same answers so they can have confidence in them, and so on. So, by default, if you compile with the Intel compiler, so I'm using the Intel Fortran compiler here, but the same goes for the Intel C++ compiler. By default, if I compile, I will get code that uses SSE2 instructions, so streaming SIMD instructions. These are quite old, they've been around for a long time, and you can tell them because you can see these things because they're using these XMM registers in the assembly code, and they're using these parallel instructions, move underline packed single and multiplied parallel double vectors. So you can see that that's the code that's generated by default, because I didn't use any compiler flags. But the Intel compiler lets me compile in such a way that my object files don't just include one code for one kind of instruction, but they let me compile for more than one. So if I use this switch here, QAX core AVX2, I'm doing this on Windows, but the same thing happens on Linux. It generates code. If I look in the assembly code, I can see that this part of the object file is using XMM registers, so using SSE2 instructions. Part of it is using AVX, it's using these YMM registers, and it's using fuse multiply adds, FMA instructions. And the way the object file works is it first of all checks this thing called the Intel CPU feature indicator, and from there it decides which of these it can execute. And how does it do that? Well, in general, it looks on the machine, checks what hardware is available. It says, do I have AVX instructions? Do I have FMA? If so, use this code. And if I don't, then use this code. This is kind of the fallback code because almost all machines have SSE2 instructions. So at runtime, there's an Intel runtime library function called May I Use CPU feature. And at runtime, the code checks these flags to find out what it's allowed to use, whether it's allowed to use these instructions or not. And it uses what it considers to be the best, which probably means the fastest. So if AVX2 instructions are available, it will use those instructions in my object file. Very good. But, so we started building mag libraries using these AVX instructions a while ago from customer demand. They said, we want these things. But then we start getting reports back saying, oh, well, you know, we're running on a heterogeneous network. We don't always know which node our code's running on. And sometimes it gets different results. And what can we do about it? Well, what that meant was that we had to find a way of avoiding using these FMA or AVX instructions. What that meant was we had to go and rebuild these mag libraries to satisfy our customers, because they were upset about getting these non-reproducible results. So we had to go through a lot of work. We have to do more testing, more QA, and the documentation becomes more confusing because you have to make sure that people know what they're using, what versions of libraries. So there's more work all around. Now, the great thing is that recently, Intel have introduced in their compiler, their latest compiler, which I think is supposed to be out sometime this month. I'm looking at Laurent to confirm that. And he's looking behind us. 17? Yeah, okay, so the pre-release version has been available and I've been testing it recently. What they've done, they've introduced a new runtime feature which checks an environment variable called Intel ISA disable. And that's checking the instruction set. And what this thing lets you do, you can set this environment variable before you run your program. And that environment variable gets checked, and it's a list of all the instruction sets that you don't want your code to use. So in the case of the NAG library, it would mean that even though our object files contain code for AVX and AVX2 and FMA and so on, it gives the possibility for us to run our program and make sure that those AVX instructions are not used. So here I've set this environment variable to be AVX, AVX2, FMA, so the comma-separated list of things. And my program is now no longer allowed to use AVX and fuse multiply adds, even if the hardware's got them. So, little experiment. I'm using C compiler now. I've got a C code that computes a dot product, very trivial code, about 5 lines long. I compile with a flag that says, I want to use SSE2 instructions only. I don't want any variations. So I can run that thing, I compile and compute a dot product of length of 100 million, and it comes back with the result, which turns out to be 99 point and a bunch of nines. Again, this is double precision. And it took 18 seconds. I recompile the same program, but this time I say I'm allowed to use AVX2 instructions, that includes FMA, but the compiler also generates code for SSE2 as a variant, without me asking it to, it does that. So I've told it I'm allowing AVX and SSE2. If I set the environment variable, if I unset it, so I'm setting it to nothing. So by default, when I run the executable, it goes and says, oh, my machine's got AVX instructions, I'll use those things. Fantastic, same problem size. The result is a little bit different because now I'm using AVX instructions. All the dot product and partial products get accumulated in a different order. So that's why I'm getting a slightly different result. It runs faster, 13 seconds instead of 18. Fantastic. But now if I set this environment variable and say, don't use all these AVX things or the FMA because I'm not accepting that I'm getting different results here. So if I set this environment variable, run it again, and now I get the same results as I originally did when I was just compiled to use SAC2. So great news for me anyway, because it's a way for us to help our customers without us having to build bespoke versions of an ag library. Time goes back up to 18 seconds. Now, it's a little bit misleading for me to show you these times, because actually if you rerun this thing many times, you'll find that these numbers are all over the place, the timing results are all over the place. And I think that's because of the power configuration of the processor, where the frequency goes up and down depending on what's going on the machine. And so these numbers can vary quite a lot. It doesn't mean that the AVX instructions are not getting used. They definitely are still getting used. Even if sometimes that AVX version takes almost as long as the SSE version. So that's great news. It makes life more predictable for all of our customers. It means that we don't have to build so many bespoke libraries, because I would say in the last 6 months, I've spent probably a third of my time actually just building special versions of NAG libraries that I didn't really want to have to build. It means that we can, all our testing gets simplified, because in the old days we used to have to run our test software on different machines, some that had AVX instructions, some that didn't, so we could be confident that both paths were getting executed. But we don't have to do that anymore, or we shouldn't have to do that anymore. Because of all this functionality is built into the compiler runtime libraries, it doesn't matter if your top-level program is being called from some other environment like Python, because the environment variable will still take effect as long as the NAG library or whatever program you're working on was compiled with the Intel compiler. This environment variable should work, so it doesn't matter how you call it at the top level. One thing to note is that this environment variable doesn't affect anything that goes on in the math kernel library. There are other methods for controlling what goes on there, and I think Cedric's going to talk about that this afternoon, if I'm not mistaken. And you might need to be a little bit careful. So for example, here, I've told the compiler that I want to generate AVX instructions only. So QX means only AVX. I run the program and it works fine. But now if I set the environment variable and say, oh, I don't want to use AVX instructions, I did it just out of curiosity, really. I tried running the program. What happens? I get an error message saying, verify that both the operating system and the processor support Intel, SSE, SSE2, and AVX instructions. So in other words, you can make it so your program won't run at all. You just have to be a little bit careful. I don't expect that that's really going to happen. That's all I've got to say. If you've got any questions, let me know. Yeah?
How is it possible to get different results running exactly the same instruction set with the same data on the same sheet?
It's possible because with the dot product example, not the dot product example I showed here, but with the dot product example that one of our customers found, it all depended on memory alignment. And the memory alignment in the main program was out of his control. And it turns out that to use SSE instructions efficiently, you need to have the memory aligned on 16-byte boundaries. And if your memory is not aligned on 16-byte boundaries, then you can't use the SSE instruction. So the compiler was generating code that, first of all, checked the memory alignment and said, is it 16-byte aligned? Fantastic, use this fast method. Is it not 16-byte aligned? Well, I have to advance a little bit along to make it 16-byte aligned and do some computation in a slightly different order. And when he ran his program, sometimes the memory that the operating system gave to his main program was aligned, and sometimes it wasn't.
Okay, so if you use, say, aligned memory allocation.
If you allocate your own memory and align it, then that won't happen. But if you don't know where your memory is coming from, then it can happen.
There is a flag to disable randomization for binaries, so you can have a predictable allocation.
Right.
Even
Okay.
if it's aligned or unaligned, you can control it.
Okay. I don't. What is that flag called?
It's in Linux on kernel, so you can. Because otherwise you have random memory allocations.
Yeah.
We can't hear anything of the question. No?
He was saying that there's a compiler flag that lets you have some control over how the memory does get aligned in the first place, which would be helpful.
So can you just go back to slides on Python and Visual C++? Were you saying it does affect, sorry, the slides on Visual C++ and Python, were you saying it was or was not able to cope with?
It doesn't. It's fine for your program to be in Python because the runtime libraries that are getting used by the underlying library are still the Intel runtime libraries because the compiler generates calls into those things. So if your main program is Python, you can still use the environment variable and it will still work. It will still do what you want it to do.
If you have a version of Python that knows.
No, it's nothing to do with Python. Sorry. I may be not being clear here. I'm talking about if you've got Python that's calling a low-level NAG library.
Oh.
Right, that's what I didn't make clear. Yeah, with Python itself, the whole different thing. I don't know. All right. Well, if anybody else wants to talk about it in the break later on. And thanks for listening.
Thank you.
The compiler side, so how to get as much as possible reproducibility with the Intel compiler. And at the end of this presentation, I will also show you with Advisor again. There is a way actually to check if you are doing some risky stuff in your application. So we are looking for several things that I will demonstrate here. And that will output you, for example, if you have usage of FMA, it will tell you how to remove those things and so on. So this is basically into size for this presentation. Okay. So let's just keep this. So that was basically the introduction here. So reproducibility is some problem that might be important for you. There are many reasons for that. Usually that also comes at some point from the management who wants to reproduce results, bitwise results, because you have guaranteed that at some point your application worked in the past and you want to be able to reproduce something that worked. Even if this is sometimes not really good reasons, but let's say that it works like that. And there are many ways and many different industries that want to reproduce results. So FSI, of course, but I was working with oil and gas before. It was the same kind of problem. And there is something that is important, and I actually saw it in the presentation earlier. So there is really a difference between reproducible and accurate. And we are going to talk a little bit about that. So why do we have reproducibility issues? well, we don't have associativity on the machines. So basically, if you are doing this operation here, I can change actually, did the first presentation on this side, so now I will do it on this side. So if you do this set of operation, so if you want an infinitely precise result, then you have 2 power minus 63 plus 1 minus 1. So this is the correct result. But on a computer, actually the 2 different lines here, they produce something that is valid. An output that is valid. And it just depends how you put the parentheses. So if you put the parentheses on the 2 first elements, then 2 to the power of minus 63 plus 1 is basically rounded to 1. Minus 1, this is equal to 0. And in the second case, you start by doing 1 minus 1, so 0. Then you add 2 power to the minus 63, then the result will be 2 to the power of minus 63. So this is mainly the reason why you see some difference from run to run or on different platforms in your application. It's because of associativity issues. So some also sources, but this is always linked at some point to those problems, might come actually from the compiler. So you have one application that is compiled with one version of the compiler, then you move to a new version, and you get different results. And that might happen actually because from one version to the other one in the compiler, we optimize new things. And then those new things might end up having different associativity in the computation, and then you get different results. So that can also be processor dependent. You might have changes that are based on the architecture. For example, we talked about AVX, AVX2. Between AVX, AVX2, Intel implemented FMA. And FMA, this is fuse multiply add. So basically in one cycle, you have the ability to do one addition and one multiplication. And the intermediate rounding is using more bits than the separate addition and multiplication, which means that you have a more precise, at some point, value when you do the FMA than when you do separate addition and multiplication. So if you compare a code that runs without FMA and with FMA, you might observe different results. And of course, usually you need to optimize at some point to do vectorization. As much as possible, use FMA because you will get a speed up out of it. So that's always a balance between getting your reproducibility but also getting your performance. So there are a few examples here. So if you compile with minus X AVX or minus X for AVX2, you have one option without FMA, another one with FMA. So something also that is pretty painful for reproducibility is this parallel implementation of reductions. So if you have OpenMP, for example, you want to do an OpenMP or TBB reduction, then you're going to hit some problems if you are not careful here. Because you don't have guarantee at some point that you will do those intermediate sums in the same order. And also something that can play a role, and this is a tricky part actually, this is the change in alignment. And I will just explain that later. So another source of variability might be differences in accuracy actually. If you change the accuracy of your math functions, then you might end up getting different results. And this is also the case with FMA. So now let's talk about good practice. So what can you do for reductions? So for reductions, if you are using OpenMP, the first thing that you need to do if you want run-to-run reproducibility, so same application, same machine, but you want to get reproducibility across different runs, you need to ensure that you will not change the number of threads. So always use the same number of threads. Then you need to export also with at least our version of OpenMP, you need to export KMP deterministic reduction equal yes. And then that will force the partial sum to be executed in the same order. And so also, yeah, same number of threads. So for TBB, instead of using parallel reduce, then you can use parallel deterministic reduce function. And in that case, you will also get your reproducibility. Again, with the same number of threads, of course. And for MPI, you need to choose topology unaware reduction algorithm if you want to get reproducibility with that kind of implementation. Okay. So another problem that you might get is actually due to alignment. So what can be the problem? Any idea what could be the problem with alignment? If you change the alignment, what should be the reason why you could get some different results? Any idea? So single instruction by itself will not make any difference. This is the same instruction. So that's not the reason why you would get different results. So the main reason actually is when you, for example, you rely on math libraries. And you might have different implementation in the PIL, in the vectorized part, and in the remainder. So usually, this is the next slide, but this is just to let you know why alignment might be a problem. You might have two different libraries, libm or libsvml, that are used by the Intel compiler to generate like exponential or any sinus, cosinus, any math functions. And so it's not the case necessarily today, but in the past, even on version 17 or 18, you might have actually different library for the PIL and for the vectorized parts. And those libraries, they have different algorithms, different implementation, different associativity. And then if you change the alignment from one run to another one, you will have actually different number of iterations in the PIL and in the vectorized body, and then different results at the end, because this is not the same algorithm if you are using two different libraries for that. So what you can do to avoid that is using malloc, for example, or POSIX memline in your code to allocate the data and force alignment. In Fortran, this is a bit different, so you can do it through the compiler. And if you are kind of too late for doing that in your application and you don't want to do it, you can use this flag, the Q no OPT dynamic align. And this one is going to ensure that there is no specific optimization done for the PIL and for the remainder. So that will be basically the same optimization as what is applied for the vectorized part. So back to the libraries. So we have two libraries with the Intel compiler. Actually, yeah. We have two libraries. One is called libm. This is the scalar implementation. This is an old one, which is not performing very efficiently. And then we also have the libsvml, which is a vectorized implementation of the math functions. So as I was saying, in some case, the compiler might decide to rely on libm for PIL and remainders, and to rely on libsvml for the vectorized parts. And this is usually when you can get some issues. And this is where you want to use this Q no OPT dynamic align flag. So there is also something else that you can do actually. Starting, I think this is with the 18th version of the compiler, we introduced this flag, -FEMF use SVML. And this one is going to force usage of SVML even for the PIL and for the remainder. So in that case, you have the guarantee that you will have the same algorithm, the same implementation, basically, for the PIL, the vectorized part, and the remainder. So you're not supposed to get any associativity issue based on alignment and on math library calls if you are using that. So no FMA. So this is actually a very special flag because you might, I guess, if you not play with this flag, you might not really understand what it's doing by default. So just you need to understand that the no FMA flag will remove FMA only on the code, of course, that you compile, not on the math libraries, not on MKL, not on any libraries that you are using. So sometimes people are kind of surprised because they use this flag, and then they check, for example, with SDE, the software development emulator, or VTune, and they still see FMA in their code. This is just because maybe you rely on libraries that are doing FMA, and that will have absolutely no impact on that. So just need to understand that if you want to remove FMA, no FMA is one way to go, but just for your code, the code that you are writing, basically, not on the libraries that you are using. Okay, so FP model precise. Who here knows about this flag and who is using FP model precise? Okay, so not that much actually. So usually this is the first flag that people are using when they have reproducibility issues. But this is not a flag actually to help you getting reproducibility. This is mainly a flag that mixes at some point reproducibility, but mainly precision things. So what it does, first, it doesn't authorize unsafe optimization, and those optimizations, they have nothing to do with reproducibility. No flush to zero, so approximation, no approximation of square roots and divide, nothing to do with reproducibility neither. This one is strong. This is a very painful, actually, element of the FP model precise. By default, it uses libm. It means that all your mathematical calls, if you are using FP model precise, they are not vectorized anymore. They are scalar. So you need to be aware of that. So there are some tricks that actually you can use to avoid using this flag. So what you can do actually, you can use assume protect parents in Fortran or F protect parents in C++ to actually force the respect of the parentheses in your code if you want to specify the associativity basically. So that's one way to actually get the only part that is about reproducibility in this flag. So be sure when you are using FP model precise that actually you know what you are doing. Okay. So also what can change from one run on one machine to another run on another machine is actually if you generate fat binaries. So when you use the compiler flags for generating code for a given instruction set, you need to be aware also about what you are doing. So if you are using AX something, by default you will generate what you are asking for, but also the SSC implementation. If you are using X, then you will only generate what you are asking for. So it means that if you take this binary and then you go back to SSE, then you will see basically the message that Mike showed earlier saying that you can't run it on the given hardware because they don't have the instruction set. And so it's possible now to control actually dynamic dispatching with what Mike presented earlier. Okay, so we'll switch quickly to the libraries. So what you can do actually if you are using mathematical functions in your code and you might want to remove FMA but still keep vectorization, you can use this flag FEMF R consistency equal true, because if you are not using that, if you are not doing that, basically if you compile, for example, with -x core AVX2 or -x AVX, let's say, and you are running it on AVX2 platform, then you will end up with AVX2 code in the maths library. So if you want to just control actually at some point dynamic dispatching, but also instructions used for generating your binary, then you need to use FEMF R consistency equal true, which will basically remove the FMA in the SVML. And you will still get the vectorization. So you take, for example, the binary with this FEMF R consistency equal true, you compile for AVX512, you run it on AVX512, you will get vectorization for AVX512. You will just not get the FMA. So for MKL, this is a bit different. So you need to use this environment variable. If you want to avoid, for example, using FMA, then you can use, for example, MKL enable instructions, AVX. So you have different way to control the dynamic dispatching of MKL. And yeah, this is something else. So you can't use what Mike presented for dynamic dispatching in general for MKL. They have their own system. So you need to use basically those environment variables here. Okay, so I can now try to show you. So is it big enough here? Okay. So I have different codes here. So we can start with FMA. Okay. So I can just show you the source very quickly. So this is a very stupid code. There is absolutely no interest here. The only interest is that we have some FMA here, basically. Okay, and now I will show you with Advisor how we can detect that your code is generating FMAs. And Advisor will also provide you some hints about how to disable the FMA at some point. So I can just show you the makefile, how I'm doing this. So I'm just calling make fp repro, and that will just basically build my binary and use Advisor survey. And then there is a script in Advisor, so that's in Python API example fprepro.py. And this script is basically checking Advisor's result directory and outputs some things related to FP reproducibility. So let me show you what we get. So now we are running Advisor. And at the end, so this Python script, so that's part of Advisor package, actually it's Python script. It will tell you, so fuse multiply add, so the use of fuse multiply add instruction over, so you have many information, you know which line was responsible for the generation of this FMA, and you should have the compiler flag somewhere. I'm probably too close. Yeah, no FMA compiler flag to disable it here. So you have also the indication how to solve this issue. Actually, we can try. Okay, now it doesn't find the FMA anymore. Because the FMA came from my code, not from any library. Okay, so there are other examples. For example, libm. So same, I can just show you the source, but the makefile is basically the same. So for the source here, there is a call to sinus. So in this case, I'm actually running two analyses of Advisor. I'm also using the trip count because if I recall, that was a bit short, and then I didn't have any guarantee that the sampling will pop out of the scene function. So I need to basically run another step. But what you have as outputs, yeah, I'm too close. So libm call present, that will tell you which function is used. And then you have some information about how to force SVML. So for example, FEMF use SVML will force usage of SVML. We can do it. Actually, I can copy it. Okay, now we don't have any call to libm. I can just show you something quickly, actually. So if you are using the FP model precise, so that will also generate call to libm, but you can actually bypass this restriction. So even if in your code you have the FP model precise, you can bypass it, and you can still force usage of SVML by adding this -f EMF use SVML. So if we do this, we should not see any libm call. Okay, so there is some warning about a call to SVML here, but there is no warning about anything about libm. So this is what we're looking for. So actually, I don't know why in the previous case it didn't trigger it, but at least you see the name of the function, so you see if this is SVML or libm, and you definitely want to avoid libm as much as possible. So we can also go maybe, I don't know how much time I have, 5 minutes. So let's go to the peel. Okay, so this code is actually generating some peel. So we have some real size and we are doing some unalignment at some point. And then we have some code here. So we are just shifting actually the address at some point. Okay, and when we run this, so the interest of this script is really to show you all the potential problems that you might have regarding reproducibility in your code. So that will not solve all the problems, but that might at least reduce a lot what you currently have. So here in that case, it will tell you peel loop present. It tells you which loop is basically responsible for it. And then it gives you some insight about what to do. So here, basically, if you want to guarantee that you will not have any specific optimization for the peel and for the vectorized body, you need to add this flag. So if I'm adding it, it will probably not change actually in the makefile. It will not change the fact that I still have a peel. So we'll still probably see the peel, we can try. But it will just, at some point, guarantee that I will not apply different optimization steps between the peel and the vectorized part. Yeah, so we still see it. So that will not remove it, basically. Okay, then for OpenMP reduction, for example, we can check. So I need to fight because the keyboard is in German. I made a mistake when I ordered the keyboard. I thought it was a US one, and then I need to deal with this German keyboard. Okay. So we have OpenMP parallel reduction here, okay, in the code. So let's see if it tries to test it. At least it was working when I prepared the presentation. So I guess we'll provide a slide if you want to test it. All the command lines, they are actually in the slides. I just didn't show you the slides, but this is right after what I presented. Okay, so then you see actually OpenMP reduction And then it tells you use can p-deterministic reduction to true and fixed number of threads and so on. Oh, also, yeah, you need static scheduling, of course. So you need to have some reproducible scheduling. Okay, so I guess, yeah, it's 44, so I'm out of time. Do you have a question? We have 1 minute. Yep.
Yeah, Cedric, thank that interesting presentation. Thanks. It's clear that FMA instructions cause a lot of trouble for reproducibility use, as I know from my experience and you described. Do you think, in hindsight, it would have, and a lot of those problems are because of the intermediate rounding that's to infinite precision, or some higher precision. Do you think it would have been sensible to have the intermediate rounding done to regular precision instead, and then you wouldn't have so many problems? Do you think that was ever considered?
That's a good thing. I think it just depends also in which order the compiler will generate the equivalent instruction, like the addition and multiplication. So that's the question, right? If we are using the same rounding as separate in the FMA?
Yeah, if you did the intermediate rounding to the same precision as what you're doing,
So I guess, I mean, that should fix a lot of issue for sure. But,
we saved a lot of messing about, I thought.
So, but I don't know.
Yeah, maybe I'd like to.
If you want
just a comment on Nick's comment. I very much like FMAs actually, because even though they do cause some issues in some instances, they are very useful to generate error-free transformations, such as everything you need to perform a multiplication and have the associated round-off error. And this is very useful in turn to generate compensated summations or dot products, or in general compensated algorithms. And I think, and this is my personal opinion, but I think using compensated algorithms is probably one way in the future we'll be able to both leverage smaller floating point numbers while still having higher accuracy than what they give us for free. And so in this perspective, I very much like that we have basically the error-free multiplication for free, thanks to the FMA.
Yeah. Other questions? Comments? Yeah. I think.
Just to go back to what you said near the start about alignment not affecting SIMD. Well, I think it's not always true, because with SSE2 instructions there are unaligned move instructions and aligned instructions. And you can't use aligned instructions on unaligned data because you get a safe fault. So that means you need to do a little bit of cleanup if the So I think it can sometimes happen. Which is what was happening in the case.
So that was the same actually on KNC also. I mean, it was not possible to load unaligned vector with unaligned loads. So so you had to align the data. But this is not true anymore. So most recent platforms. Thank you.
Okay, hi everyone. Everyone is hearing me?
Yep.
Okay, nice. So I'm Wilfred Chasherman. I'm working at NEO, and I will explain why we have the Aldrin logo just after, before starting the presentation. After all this talk about numerical instabilities, debugging, and finding them, and so on, and this talk about reproducibility, we see that there also is an opportunity in the field of floating point, is enhancing the performances through reducing the precision, but only where it doesn't affect the final result. So to do that, we rely on the tool presented before by François. Okay, so very quickly, so I said I'm from NEO. You will have, these slides are mainly for you to keep after that, so I will go very fast. I'm from NEO, which is a consulting company based in Paris. We are about 200 people working, half our turnover is in the FSI, and we are providing services from the C-axis consulting for the CXOs to help the operational manager and especially in IT development. And Alduin is a brand we created dedicated to advanced computing technologies, which has HPC, AI, cloud, and big data. We provide services in insurance, finance, industry, retail, and life science. Basically, what we are most famous for is we take the performance consideration from the moment a user clicks on this graphic interface or on this keyboard anywhere, and then a lot of things happen. The computation might be distributed on the grid, on the cloud. Maybe there is a whole infrastructure starting building after the click and so on, and after a while, the results come back to the display. Well, we are focused on optimizing the performance of the whole chain that allow these results to be produced. And so we are in this team 27 consulting people with 11 PhDs. So now we get into the topic of this presentation. We will first see why we need to pay attention to the precision while optimizing a software, and we will see it through the consideration of hardware. We'll see it through hardware consideration. Then we will have a very small reminder of floating point arithmetic, but we have seen that before, so I will go very quick about this. Then I will make a very short presentation of an algorithm. I won't show you any pseudocode or code. I will just tell you that there are some parts in this algorithm, and we will see how we can use floating point analysis to improve its performances. So first, the hardware considerations. This graphics represents the computing power of the best Intel processor on the market for each year since 89. No. So what we can see is we have different elements to compute to determine the compute power of a processor. We saw the formula in the presentation this morning. We'll have the frequency, which is the orange line. And this frequency says the number of cycles you will have in each second. The orange part represents the number of operations you can do in one cycle. Here, you needed 20 cycles to make one floating point operation. Then, starting from the Pentium processor, you could use one floating point operation per cycle. And now, using SMA and the fact that we have two compute units in the core, we can perform 4 floating point operations per cycle. Then, you have the number of cores, which is increasing, of course, since 2002. And on top of that, you have the all potentiality of the SIMD register. The registers, they have a fixed size, which means that if you're using a double precision, you will get this increasing. And if you have single precision, you can double again the performances you can reach. So the question that we will have to wonder is, can we achieve getting this twice performance without losing the precision of the results? Part of the answer would be the compensating algorithm we saw before, not only. So increase in frequency is the free lunch. You don't have anything to do to benefit from it. The operation output, it's almost free lunch. Sometimes for some generation, you just need to recompile. The multi-core part, then you need to parallelize. So you need to change your software. And for the SIMD, you need to vectorize your code, which might be the hard part because it's very low level and it's rely on both the algorithm and the data structure. Then if we look the other way, to make a computation, you need to have some compute units, but you also need to have data. The data are in memory. So if you compare the performances, which is in orange, compute power available, the memory bandwidth in red, what we can see is they are getting, the difference is getting wider and wider. And if you look the number of floating point operations you need to do to digest one operation, basically on the most recent, most powerful processor by Intel, you need to make 76 floating point operations to be able to reach the roof line we saw this morning. So which means you need to do a lot of computation. Most of the algorithm will be compute bound, will be memory bound, except if you use the cache efficiently. But again, the cache is limited in size. So if you put 32 bits data in the cache, you can fit twice the data. So you can basically achieve a better data usage. So why we may want to decrease the precision of the algorithm we want? It may be to reduce the memory impact and allow to the execution for bigger programs, better use of the cache hierarchy, and better use of the memory bandwidth. It also has an impact on the computational power because we can use better the SIMD register, and it will also be useful when we think about accelerator. Tomorrow we'll have talks about one API. If you look, for instance, at current Intel GPUs, they can perform 4 single precision operations against 1 double precision operation. So it's not a 2-fold that we would have as on CPU, but a 4-fold acceleration. Just a very quick reminder about the floating point arithmetic. So this is the binary representation of a single precision and double precision number. What we can see is doing from single to double precision, we have a wider exponent, which means we can represent much smaller and much bigger numbers. And we also have a wider fraction part, which means we can represent numbers with better precision. It also means, in both cases, that we have a finite representation. So it means that some numbers have no representation in binary format. You cannot represent 0.1. It doesn't exist. Just like P doesn't exist in our decimal structure. You can have some cancellation. You can have a lot of errors that have been presented before. And also we lose a lot of properties, of arithmetic properties that we used to use. For instance, addition and multiplication are not associative. Depending on how you put the parentheses in your code, you won't have the same results. They are not distributive. It means that if you have A multiplied by B plus C, it's not the same as A multiplied by B plus A multiplied by C, which is something we used to do when we are thinking with real world. And division and multiplication are not reciprocal. Not only because the division might be approximate, as we saw in the previous presentation, but also because the result of the division might not be precise, might not exist. If you divide 1 by 10, you have a result that doesn't exist in binary format. So if you multiply it again by 10, you won't get 1. You cannot, because you have lost some bits. So this is just to prevent why we have some issues and why we need to pay attention to floating point arithmetic, which we usually don't. Now I present the principles of a very specific kind of simulation that might occur in FSI, which is the least square Monte Carlo simulation. Usually when we perform, so this kind of simulation has been described by Longstaff and Schwartz in 2001. And the idea is to be able to evaluate American option by backpropagating the results, the decision from the end. I will explain just after. The basic implementation we use on the description after was by Gilles Deville, which is a professor in Paris, and it has been widely optimized and used for CPU, GPU, and so on and so on. So it's a very small, but with a lot of interesting things inside. As the difference between this paper, if you look it or if you know it, in this software we have 2 assets simulated. We have a regression with 3 regressors, which means it's a level 2 polynomial, a degree 2 polynomial, and we're using 50 types per year. So the steps of this algorithm is first, we need to generate the price path. As in any classical Monte Carlo simulation in finance, we first generate the random numbers, then we generate the underlying values thanks to these numbers. When we have generated all these numbers, we have the backward induction phase, which means that we go from the end. At the end, we know the value of the underlying, so we know if the American option, the put, should be exercised or not. So we can evaluate the cash flow generated by each pass at the end. As we know this cash flow, we can go one step behind and see, okay, now knowing the future cash flow, is it a better situation now or should we wait? And so on and so on, we can go backward. We can't do that at the beginning because we don't know the cash flow. So we have to go backward. And doing this, one of the steps is to make a regression. This is done to, how to put it? If we were not doing this regression, we would have to generate a first set of paths to estimate the future, and then for each time step, we would have to generate a new set of paths so that we don't we have independent paths to rely on. We use a least square approach just to simplify it and to do less computation. Just keep this in mind for now. We have a regression in the middle for each time step, and at the end we have the aggregation of the results, which is basically the sum of all the results from each path. We can use it to compute all kinds of indicators about the price. So how, given a code, how will we use a floating point analysis to improve the performances? Basically, the approach is quite straightforward and standard. First, you need to define your test case. How do I validate that my code is providing the good results? The test case should cover all the range of values that your algorithm will be using. And it's basically the same test case that you would need to validate any evolution of your code, any evolution of your algorithm. Then we want to improve the performances, so we need to identify the hotspots. So you can use something like VTune or something. Look for the memory bottlenecks, look for the compute bottlenecks. In this part, it might be interesting to reduce the precision. If you have some memory bottlenecks, you will want to reduce the precision of the stored values, because this will consume the memory bandwidth. If you have a compute bottleneck, then you will have to, you need to reduce not only the precision of the stored values, but also the precision of the computation. If your bottleneck is only the memory, you can still compute in double precision, you need to store in single precision. And then you can use your test case to validate if the results are good or not. In our case, we wanted to have 4 digits, all the same for all the test cases. And the last part is the part where we have tools that can accelerate the process. They help you identify the unstable location. So if you reduce too much, they can tell you, oh, this is the place in your code where you are losing accuracy. They can help you looking for profile the loss of precision, telling you this is the part and this is how much you lose at each iteration, at each time step. And they can automate the trials and error process without recompiling, as we saw just before. So I just mentioned Interflop. Interflop, as François told before, is a currently French consortium for floating point analysis. I hope that very soon I will be able to remove this parenthesis. And we have, it's been launched by a few companies, including the Intel Exascale Lab and a few universities. And it provides 5 front ends. One is based on compiler, so you take your code, you compile, and then you can call any backend that I will introduce just after. You have Vero, which is another front end based on Valgrind that François introduced before. You have Fluctuate, that is a processor emulator, so it's another kind of way of instrumenting your execution. And Padlock, which is a bit like Vero, but not based on Valgrind. It's based on another software called Dynamo Rio, but it does the same. It takes a binary, and then it will change the instruction sequence from the binary. This front end benefits from a common interface for floating point operation overloading, and this interface allows for different kinds of backend to be used. You can have a noisy computation, changing the rounding mode, adding a random noise, so you don't change only the last bit, but maybe the 10 last bits. And you can even emulate a lower precision. In 64-bit double precision element, you can emulate a single precision computation. And you also have some tools that can help you to locate the errors, to analyze the error propagation, and so on. And we also have another kind of tool which currently is only available at the source code level, which changes your compute type, be it float or double, by another kind of element, which will perform three computations for each operation, one running up, one running down, and one running random. So you can have lively during your execution, how much precision have I lost? How much digit have I lost? But this is only available at the source level, so you cannot use it if you're calling another library. So we plan on integrating this into our backend. So when you use data debug, I won't show you how you use it. It's very straightforward, but if you look on the Vero documentation, it's very straightforward. But at the end, what you will have a lot of directories. In each of these directories, you will have the results of your test. And what is interesting is the determine directories, in which of them you will have a file listing the elements that should remain in double precision. And so in our code, it says that the LDLT resolution required for the version should remain in double precision. I cannot change that. Maybe there are a lot of other things I can change, but this one should remain in double precision. And as you can see, you don't have so many of them here. So it's very easy to say, okay, this one will remain double, the other one I can put in single. It won't be exactly straightforward because you know there will be, as it's stochastic, you might have some exceptions, but it's a first step, and then you can use the rule and analyze, okay, this is the place where I lose the precision, as we saw before, and so on and so on. Basically, what we saw, we observed, the main bottleneck was the computation of matrix, a dense matrix computation. But this matrix is very strange because it's for computing the regression. It's very narrow. So we didn't use MKL or something else. It was less efficient than writing the 3 loops required. But to reduce the cost of this, thanks to the analysis, we know that we can have the matrix stored in single precision. We have different variables to the POW and exponent function. Most of them can be done in single precision. Not all of them, most of them. We have a lot of arithmetic operations to generate the price path. Again, we have, thanks to our analysis, we know where we should not get to single precision. So most of them we can have in single precision. And in the backward induction, we saw that no operation can be done in single precision. If we perform single precision operation in these steps, then we will lose precision at the end. The only thing that we can do is store the results in single precision, but all the intermediate computation have to be done in double precision. There is no vectorization in this code. There is no multi-threading. In a proper application, you will have the path distributed across different computers, different cores, and so on. But in the results I will show, there is no vectorization and no multi-threading. And still, what we can observe is that going from double precision to mixed precision, we will have an average acceleration of 2. So I showed you with a different compiler. This was a very huge surprise that the last version of ICC provides such good results compared to the 2 other ones. I haven't been able to investigate yet why. But when I did the same experiments about 1 year ago, I didn't observe this difference, so I will need to understand why. And when going to the mixed precision, what we mostly gain is we were able to better use the memory bandwidth and the cache usage. It's the same as what Cedric showed this morning with the roofline presentation, when he said that there was one point that needed to be moved to the right. That's basically what we've done by changing the precision of the computation. So to conclude, yes, that's something we need to have numerical validation tests for our code, and numerical validation test means to have acceptance criterion. is this a good result or not? Okay, I've changed maybe the last bit or the last 2 bits. Is it still good or not? That's something that has to be answered. Not currently the answer, the default answer is, okay, I want the same binary reproducibility. But it won't last long. At some point, we will need to be able to check this from mathematical or from a business point of view. Simply because the code lifecycle changed the results. We change the hardware, we change the results. We change the order of operation in the code. For any reason, when you change, you make an evolution in your code, you might change the order of operation. The results might change. And you might want to change the random number generator. It has the same statistical properties, but it's much faster. You want to use it. How do you validate your results? This question is very important. I think hasn't been addressed enough as of today. But if you do this, if you have the tools required to validate the evolution of your code, then you have opportunities to explore, you can explore new optimization opportunities. You can use the tools like the Delta debug and so on, and they will help you to assess the floating point stability of your code. They will help you identify the origin of the instabilities you will have found. And as you will have identified them, you will be able either to correct them thanks to compensated algorithm, or to identify optimization opportunities while decreasing the precision. If you have any questions. Yes. I think there is a micro somewhere. Yes.
Thank you for a very interesting presentation. Do I understand correctly that basically as soon as you need to test a particular algorithm in terms of stability to precision reduction, you basically use some kind of so